Dear students, welcome back to a new mathematics session. In today's session, we shall discuss problems from the miscellaneous exercise. Let's move on to the topic. Let's begin the first question from the miscellaneous exercise. Decide among the following sets which sets are subset of one another. A is equal to set of x such that x element of R and x satisfy x square minus 8x plus 12 is equal to 0. B is equal to set of 2, 4, 6. C is equal to set of 2, 4, 6, 8 and D is equal to set 6. So B, C and D, okay, no problem because it is easily identifiable elements are there. But when we check A, it is in set builder form. We are quite familiar with this type of questions. Just we have to solve this quadratic equation. Then we will get the solution. With that solution, we will be making set A. Question is, which among the following sets are the subset of one another? Means, first of all, you have to write it in proper format. Then you have to check which set is a subset of another set. So we have to compare two sets and we have to check whether these two, one is a subset of another or not. Subset definition we know. If A is a subset of B means all the elements of A should be there in B. If A is a subset of B means all the elements of A should be there in B. Then we can say that A is a subset of B. So first of all, let's go for writing A in roster form. This is the statement. A is equal to set of x such that x element of R and x satisfy x square minus 8x plus 12 is equal to 0. So let's take this quadratic equation. X square minus 8x plus 12 is equal to 0. So this is quite familiar for us. In the bridge course also we have discussed this type. We have to split this middle term. Middle term splitting in the sense we have to find out the product and sum. See, product here, which one is the product? Product is the first coefficient of x square and here constant term. Means here it is 1 into 12, that is 12. Our product should be 12. And next is the sum. Sum is the middle term. So sum is minus 8. So that is what the condition is here. So we have to find out two numbers whose product is 12, sum is minus 8. Numbers, it should be quite clear because sum is negative and the product is positive. So both should be negative. Two numbers both should be negative. So here the numbers are minus 6 and minus 2. Minus 6 and minus 2 if you take, when you add minus 6 and minus 2 will be getting minus 8 and when you multiply these two will be getting plus 12. So we are going to split it in the middle term, that is x square minus 6x minus 2x plus 12 is equal to 0. These minus 6 and minus 2 we have used for splitting minus 8. And the first two terms if you check there is x common. And the second two terms if you check minus 2 common. We can take the common outside. So first two term x if you take, x square, x going out means x balance. From here x going out means 6 balance. So x into x minus 6. And in these two terms there is 2 common, minus 2 common. Minus 2 if it is going out, x will be balanced. From here plus 12 minus 2 when we take out as common factor, 12 divided by 2 is 6. So here 2 minus will be there in 1 plus. So 1 minus going out means the remaining 1 minus will be there. Minus into minus plus. Here you can see x minus 6, x minus 6. X minus 6 is common. Little bit of calculation we have to do here. So the first two terms, first term x minus 6 we can take out. And in the first term from here x minus 6 going means there is x balance. So that balance we can write here x. Then from the second term x minus 6 going means minus 2 will be balanced. So this is the factorization. That is equal to 0. And from here x minus 6, x minus 2 is a product. Product means any one of the quantities must be 0 or both should be 0. Means x minus 6 should be 0. That means from here if you calculate x will be 0 plus 6 is 6. Or else we can go for another one, another product we can take, that is x minus 2 is equal to 0. X minus 2 equal to 0 means x should be 0 plus 2. So that is 2. So our answers are, our solution is x is equal to 6 and x is equal to 2. Directly we can write here a is equal to set to 6. From here directly we can write. But this much calculation we have done, those who are facing difficulty, you go for this. Or else directly from here we can write a is equal to set to 6. Then B is C, D we can write. A is set to 6, B is set to 4, 6, C is 2, 4, 6, 8 etc. D is set to 6. And here C is an infinite set. And first of all let's take A. And we have to check A with other sets. All the elements of A are in B. You can see 2, 6. 2 6 here also. So all the elements of A are in B, so A is a subset of B. Next, A you compare with C, all the elements of A are in B, so 2 6 here also 2 6. So all the elements of A are in C. Okay, sorry, all the elements of A are in C, that's why A is a subset of C. But A and D, when you check, you see here A is having 2 elements but D is having only 1 element, so we cannot compare A and D for subsets because all the elements of A are not in D. That's all with A. Next we can go with B, 2 4 6. B we can compare with C, so 2 4 6 it is there in C as well, so all the elements of B are in C, so B is a subset of C. Next is 2 4 6, here D is having only 6, only 1 element, we cannot compare. And B, if you compare with A also, you can check 2 4 6 3 element, but A is having 2 element. All the elements of B are not in A, so B is not a subset of A. So that's all with B. Next we can go with C. When we compare with C, surely C is an infinite set. You can see 2 4 6 8 etc, infinite number of sets. All other sets are finite, so surely these elements of C will not be there in other finite sets, because all other elements are having countable number of elements, but C is having infinite number of elements. Surely we cannot compare with any other sets, so C is not a subset of any set. Then when we take D, you can see here D is set 6, so set 6 is having D is having only 1 element, that is 6, so it is there with A, and the same element is there with B also, and the same element is there with C also. Means D, all the elements of D is in A, so D is a subset of A. And next is all the elements of D are in B, so D is a subset of B. And again all the elements of D are in C as well, so D is a subset of C. So this is the way we calculated. Okay, move on to question number 2. Question is, in each of the following determine whether the statement is true or false. If it is true, prove it. If it is false, give an example. So here, in each of the following determine whether the statement is true or false. We have to verify whether it is true or false. We have to check whether it is true or false. If it is true, we have to give the proof. If it is false, we have to give an example. Through an example, we have to prove that it is false. First question, if X element of A and A element of B, then X element of B. See, while reading itself, it should be very clear about this one, this statement. X element of A. X is a particular member of a set. Okay, X is a particular element or a member of a set A. And the set A, here this capital letter A we use for representing sets. Set A is an element of another set B. And then this element what we have taken, a particular element which is a member of A, must be an element of B also. That is what the given statement. Once again, one particular element we are taking from a set, that is X element of A. A is our set, X is the element of that particular set. And this set is having an element of another set B. This set is a member of another set, that is set B. Then this first element what we have taken, X, is an element of B. That is what the statement says. So you have to go through this statement first very clearly, then only you have to go for stating whether it is true or false. So let's take a set A. This is our set A. A is equal to set of 1 2. 2 elements are there. Then here X element of A, that is what our first statement. X element of A means one particular element you are taking from the set, implies 1 I am taking. 1 is an element of set A, that is set of 1 2. Then A element of B, here A element of B is mentioned. A element of B means our A is set to 1 2. So implies our set B will be set of 1 2. You can see set of 1 2 is inside the set. Set of 1 2, then 3 4 5 other elements. Here A element of B, you can see A element of the set B. A is our set of 1 2. Set of 1 2 3 4 5. This is our set B. The set B is having inside another set, that is our A. Then 1 is not an element of set 1 2 3 4 5. You can see we have to check whether X element of B or not. X is our particular number we have taken here, 1. So we have to check 1 is an element of B set or not. 1 is clearly not an element of this set. Even though 1 is there here, but it is a complete set. Set 1, 2 is a particular element there. Set 1, 2 is a whole element there. So this 1 is not a part of this set B. Okay, so 1 is not an element of set of 1, 2, 3, 4, 5. Sometimes you may feel that 1 is here. No, this 1 is a part of this set A. Okay, so here 1 is not an element of set of 1, 2, 3, 4, 5. So the given statement is false. So given statement is false. We have given the example also. Through an example only we have proved that the given statement is false. Next is, if A is a subset of B and B element of C, then A element of C. Remember this statement again. A is a subset of B. A is a subset of B means every element of A should be there in B. And B is an element of another set C. Set B. This is set B. Set B is an element of another set C. Then set A element of set C. That is what the given statement. Let's take, let A is equal to set 1, 2, a particular set. Here all capital letters we have used, means this capital letters representation means it is a set. All are set. A is a set, B is a set, and C is also a set. So here A I am taking a particular set of 2. Then B is I am taking set of 0, 2, because A is a subset of B. Every element of A should be an element of B. That is the way we have to take the sets A and B. You can take any example, it's not a problem. While taking examples, you must be well aware that A given conditions, that is A is a subset of B. A is a subset of B means every element of A should be there in B. So 2 is there in B. So A is a subset of B. Then C I am taking. C is, when you check C here, C, there is a condition given. B must be an element of C. B is our 0, 2. So when you take C, set of 1, then set 0, 2. 0, 2 is our B, then one more element 3. So remember, when you take C, B should be an element of C. What is B? B is our set. So set 0, 2 should be there inside there. Set 0, 2, any other 2 elements you can put 1 and 3 I'm taking. Then set 2 is not an element of C. You can see here A element of C or not. A is what? Set 2. So set 2 clearly not there in this set. Elements are 1, set 0, 2, 3. These are the elements. 1, set 0, 2, set 1, set 0, 2, 3. These are the elements of C, set C. But here we are asked to check whether A is an element of C. What is A? Set 2. Set 2 is clearly not inside of this set C. So set 2 is not an element of C. So hence A is not an element of C. What is A? A is set 2. So A is not an element of C. So the given statement is false. So here only one thing you must take care while taking the sets A and B. This condition should satisfy. A is a subset of B and B element of C. Next is third one. If A is a subset of B and B is a subset of C, then A is a subset of C. A is a subset of B means every element of A should be there in B. And B must be a subset of C means every element of B should be there in C. Then we have to check whether A is a subset of C or not. Here A I am taking a particular set 1. Then B I have to take. While taking B I have to be careful. Every element of A should be there in B. So B will be set 1, 2 means element of A is there already with B. So A is a subset of B. Next I have to take C. So here B is a subset of C and then C I am taking one more set, that is set of 1, 2, 3. A is a subset of C. Here you can check when I am taking C set of 1, 2, 3. We have to check A and C now. A is having one element, that is set 1. Then here it is 1 is the element of A and the same element is there in C. So every element of A is there in B. All the element of A are in B. So A is a subset of C. So the given statement is true. The next one, number 4, if A not a subset of B and B not a subset of C, then A is not a subset of C. Just opposite of this statement, let's check. Let A is equal to set 1, 2. A is not a subset of B. Here A is a subset of B means very carefully we have taken A and B. Means every element of A should be there in B. But here that condition is not there. A is not a subset of B. means A I have taken set 1 2 and B I am taking set 0 6 2, means no element of A is there in B. Clearly A is not a subset of B. Then B is not a subset of C. That means C will be taking as 0 6 8 B element, and here it is 0 6 is there but 8 is not there. Other elements we have included 0 1 2 6 9. Clearly all the elements of B is not there in C, so B is not a subset of C. First condition is satisfied. First two conditions. Then A is not a subset of C. You can see here A 1 2, element of A is 1 2. Same 1 2 is there in C, means all the elements of A are in set C. That means this statement is wrong. So but all the elements of set A are in set C, means A is a subset of C. So the given statement is false. Next is question number 5. If X element of A and A not a subset of B, then X element of B. And question number 6. If A is a subset of B and X not an element of B, then X not an element of A. Next we shall discuss question number 3. Let A, B and C be the set such that A union B is equal to A union C and A intersection B is equal to A intersection C. Then show that B is equal to C. Here two conditions are given. A union B and A union C are equal. A intersection B and A intersection C are equal. We have to prove that B is equal to C. Set B equal to set C. So before start solving this question, please make sure that you are well aware of the concepts which we have used up to exercise 1.6, or else you have to make it clear and come back here. If you are not doing so, you may find it difficult to solve these type of questions. So let's begin. This is our first condition. A union B is equal to A union C. I have written, and on the left side and right side I am taking intersection with B. Taking intersection with B means A union B intersection B. A union B intersection B. I have taken one intersection B on the left side. The same intersection B, then same operation I am doing on the right side also. So if you do the same operation on left side and right side, since it is an equation, it will be balanced. There is no value change. Now A union B intersection B. Let's check what is A union B intersection B. So here only we are going to use our Venn diagram. So we know that A union B means, see, this is one circle, we can mark it as A, and another circle means this one we can take it as B. And A union B means we know that it is common portion for both A and B. We will use another color to shade this one. So this is the portion for A union B, means all A and B together we will be taking, and this is for A union B. Now we are asked to check A union B intersection B. Intersection B means common portion for B, and A union B which is common for B. B portion is here, you can see here. So this is B, and A union B intersection B. A union B intersection B means A union B is the entire circles, A and B circles, common for B. Common for B means this portion. So both the shading portion is coming here, means that will be equal to B. So A union B intersection B is equal to B, equal to, here when you check A union C intersection B. So just A intersection B, just like how we remove the bracket, that's all. When we are doing algebraic expressions, how we remove the bracket, same way you can do it. A intersection B, it's written. Then this symbol union B intersection C, or C intersection B, C intersection B. If you want, I will just draw and show you. That is A intersection B. Next is, this is the symbol you have to use, union C intersection B. This is what we have written here. Okay, then let's label it as equation number 1. Again I will take the same condition, that is A union B equal to A union C. When I take A union B is equal to A union C, here I have taken intersection with B. Now I will take intersection with the C, because I need B is equal to C. First B we have taken, and the next C I will be taking. So in taking intersection with the C, A union B intersection C is equal to A union C intersection C. Just taking intersection C on the left and right. Now you can check A union B intersection C. That we have to remove bracket like this, and here you can check A union C intersection C. Here we have written A union B intersection B. By using the diagram we have taken as B. Okay, A union B intersection B we have taken as B. That means the same way only here also. A union C intersection C. A union C intersection C is clearly C. Only left side we have to change. That is like this we have to change. A intersection C union B intersection C. So A intersection C union B intersection C that we have written is in, that is equal to, when you check here right side we have already discussed, A union C intersection C. A union C intersection C is clearly C. Then this is, when we rearrange it, A intersection C union B intersection C. Here instead of A intersection C I have written A intersection B because it is given to us. A intersection B and A intersection C are equal. A intersection B and A intersection C are equal. So A intersection C we have replaced and substituted A intersection B. The remaining things are same. Union B intersection C is equal to C. That we can label it as equation number 2. Now 1 and 2 clearly you can observe. On the right hand side of first equation, A intersection B union C intersection B. Of course C intersection B or B intersection C both the same. And here on the left side of 2 also same. A intersection B union B intersection C. That means here RHS and here LHS will be equal. That means B and C clearly will be equal. So here when we write by using 1 and 2 we can tell that B and C are equal. Hope it is clear. Just to keep it in mind that first we have to take intersection with B, this B. Next we have to take intersection with the C in the given condition A union B is equal to A union C. Next is only the normal calculations. Only this is a portion, little bit of explanation is needed. I hope it is clear for you all. Next we shall discuss question number 4. Question is, show that the following 4 conditions are equivalent. First condition is A is a subset of B. Second condition, A minus B is equal to null set. Third condition, A union B is equal to B. Fourth condition, A intersection B is equal to A. Here we have to prove that all these 4 conditions are equivalent. How do we prove? We have to prove first condition is equivalent to second. Second condition is equivalent to third. Third condition is equivalent to fourth. Then we can say that these 4 conditions are equivalent. First of all, A is a subset of B. Means we are going to take first and second. First condition is equivalent to second condition we are going to prove. What is our first condition? A is a subset of B. A is a subset of B means every element of A should be there in B. This means that all elements of A are in B. When we use Venn diagram to represent, every element of A should be there in B. Means A is inside B. B set is there and A set if you take it will be inside B. Means every element of A should be there in B. And from this Venn diagram we can say that A has no element different from B. A is having no element which is different from B. B may have some elements which is different from A. That's why B is bigger. But A is having no element different from B. Means A minus B. A difference B is a null set. So that is what our second condition. So the first condition and second condition are equivalent. Then we are going to show the second condition and third condition are equivalent. What is our second condition? A minus B is a null set. Means A has no elements different from B. From here itself it is clear that A has no element differ from B. That means we can say that all elements of A are in B. Or whatever elements we take from A, it will be there in B as well. Then we can say that A union B is equal to B itself. Here itself it is quite clear. If you take union of A and B, we will be taking both the circles together. But both the circles together means one circle is inside another one. A is inside B. That means B alone taking is enough. So A union B is equal to B. That is our third condition. Means second and third are equivalent. Now we will be going for third and fourth. Third condition is what? A union B is equal to B. So A union B is equal to B means all elements of A are in B. All the elements of A are in B. That's why A union B, when we take together, we are getting B set. This means that the common elements of A and B must be the elements of A. Means common elements of A and B. When we check here, B set is there, that is the bigger circle, and A circle is there, that is the smaller circle, and the smaller circle means A is inside B. Here the common elements of A and B. Common elements of A and B means this dark blue shaded one. That is a common element for both A and B. Both A and B elements must be the elements of A. So this is a common portion. When we see the figure, it is clear because the smaller circle is inside the bigger circle. So the common portion is this portion. For both small and big, the common portion is this circle, dark blue shaded one. So the common elements of A and B must be the elements of A. That means we can say A intersection B. That is a common portion or common elements for both A and B. That is equal to A. Now that is our fourth statement. Now we have proved that third statement is equivalent to fourth. So first statement we have proved equivalent to second, and the second statement we have proved it is equivalent to third, and the third statement we have proved it is equivalent to fourth. So all the four conditions are equivalent. That is what we have proved here. Next we shall discuss question number 5. The question is, show that if A is a subset of B, then C minus B is a subset of C minus A. Here given condition is A is a subset of B. Then we have to prove that C minus B, the difference between two sets C and B, is a subset of C minus A, the difference between C and A. First of all, let's take the given sets as per our assumption. A is equal to set of 1, 2, and here the condition is A is a subset of B, means all the elements of A should be there in B. Means when you take A, we have two elements. When we take B, it must be careful that all elements of A should be there in B. So here set 1 and 2 is there, so that elements are here 1 and 2 in B also. Set B is equal to set of 1, 2, 3, and C is set 1, 2, 3, 4. This is the way we have to take set A, B and C. A must be a subset of B. And here C minus B we have to calculate. C minus B means elements of C which are not in B. Elements of C which are not in B means C minus the common element, and C is here set to 1, 2, 3, 4, minus B is set to 1, 2, 3, means we have to remove this 1, 2, 3, that is a common element. When we remove, we will be getting only the balance element set to 4. C minus B means elements of C which are not in B. 1 is there, we cannot take. 2 is there, we cannot take. 3 is there, we cannot take. Only 4 is not there. So that is the element of set to C minus B. Next C minus A we can take. C minus A means set C is set to 1, 2, 3, 4, minus A is set to 1, 2. Elements of C which are not in A. So 1 is there, we cannot take. 2 is there, we cannot take. 3 not there, we can take. 4 not there, we can take. So 3 and 4 we can take. So that is set 3, 4. Here what we have to prove is C minus B is a subset of C minus A. Means all the elements of C minus B should be there in C minus A. You can see here C minus B is having 4. Set to 4 means the element is 4 here. The same element is there in C minus A also. Set to, inside the set there is 4. Means all the elements of set C minus B is there in set C minus A. That means we can say that C minus B is a subset of C minus A. Hence the proof. Here only the thing which you need to keep in mind is just to take these sets A, B and C. You have to make sure that A is a subset of B. Move on to question number 6. Assume that P of A is equal to P of B. Show that A is equal to B. So here our assumption is given P of A is equal to P of B, means this is our condition. P of A is equal to P of B. P means power set. We know how to make a power set. The set of all subsets together we can call it as a power set. All the subsets we have to write of a particular set, then if we collect together and form a set, then we will get a power set. So power set of A is equal to power set of B. Then we have to show that set A is equal to set B. Here how do we prove? That is, in order to prove A is equal to B, set A is equal to set B, if you want to prove, we should prove that A is a subset of B first of all. A is a subset of B means all elements of A is there in B. That is, A is a subset of B. That is what we are going to prove first. Same way we have to prove B is a subset of A as well. Means B is a subset of A in the sense all the elements of B is there in A also. That is, B is a subset of A. Now When we go through these two definitions, means A is a subset of B means all the elements of A is there in B, and here when we check all the elements of B is there in A also. That means A and B should be equal sets. Then only all the elements of A will be there in B and all the elements of B will be there in A also. So this is the way we are going to prove two sets are equal. Keep it in mind, if you want to prove two sets are equal means we have to prove that they are mutually subsets. Means A is a subset of B and B is a subset of A as well. That is the way we are going to prove. Here A element of P of A, we are assuming A means it is a set, capital letter we are using A. So A element of P of A. P of A means set of all subsets. Set of all subsets of A. So one particular set we are taking, that set is an element of P of A, means A element of P of B as well, because P of A and P of B are equal. P of A and P of B are equal means one element if you take from P of A, the same element will be there in P of B also. Reason, P of A and P of B are equal, their power sets are equal. Here, if set A is in power set of B, set A, as I mentioned before, this is set A is in power set of B means power set we know that it is a collection of all subsets. Collection of all subsets. That means A is a subset of B. So power set of B means P of B means it is a collection of all subsets. So subsets A element of this set means A is a subset of B. So A is a subset of B, that we can write it as A subset of B. This is what the first statement we have proved, A is a subset of B. Next, in the same way we can prove that B is a subset of A also. If you take another element B, the same way if you proceed we will get B is a subset of A. Now as we have mentioned before, we have proved A is a subset of B as well as B is a subset of A. Means it is possible only when A and B are equal sets, because then only all the elements of A will be there in B and all the elements of B will be there in A as well. So A is equal to B, that is what we have proved here. Once again, let me explain this one. First of all, we have to take a particular set, that set A. A is a member of P of A, power set of A. Power set of A means all the subsets of A are collecting together. That is called the power set. From there, one element is A. A is a set. And A element of P of A means since P of A and P of B are equal, A element of P of B as well. A element of P of B means A is a subset of B, because P of B means it is a collection of all subsets of B. So A is a subset of B, we can prove. A is a subset of B. Similar way we can prove that B is a subset of A as well. Since A is a subset of B and B is a subset of A, when we combine together, it is possible only when A is equal to B. Therefore, we can write A is equal to B. Next, we shall discuss question number 7. Is it true that for any sets A and B, P of A union P of B is equal to P of A union B? Justify your answer. We have to check whether P of A union P of B is equal to P of A union B. Here P of A and P of B stands for power sets of A and B. Power set of A means set of all subsets of A together we call power set of A. Set of all subsets of B we call it as power set of B. And set of all subsets of A union B we call it as power set of A union B. So let's take an example and find out. Here A is equal to set of 0 1, B is equal to set of 1 2. Two sets we have taken. Then A union B, when we take A and B together, that is 0 1 2, we have written A union B. Next is P of A union B. P of A union B means we know that set of all subsets. First there is phi is a subset of this set. Next is single elements we will be taking as sets. That is set 0, set 1, set 2. Single elements we have taken. Next two elements, 0, 1, that is one element. Again 1, 2, another element. Next is 0, 2, that is first and last element we have taken. So first element, one element we have taken, two elements we have taken. Now only one option balance, that is the entire set, that is set 0, 1, 2. This is the power set of A union B. Power set of A union B, how do we calculate in the sense? First we have to calculate A union B, then we have to write the subsets together in a set notation, that is called P of A union B. So first part is clear. Then Next is P of A, we are going to write power set of A. Power set of A means, as before, null set is a set of subset of every set, so that we have written. Next is single elements, that is set 0, set 1, we have written. Next, the entire elements, that is two elements together, that is set 0, 1. This is P of A. Next is P of B, we will write. P of B means, as before, we will start first with a null set. So null set we have written. Then next is single element, that is set 1 and set 2. Next is the entire set of 1, 2. The power sets are ready. Next is P of A union P of B. P of A union P of B means these two sets together. Means phi is there common for both, so we will be writing only 1. So set 0 that we have taken, set 1 we have taken, set 1 2 times is there, we will write only 1. Next is set 0 1, only 1 time, that we can write. Next is set 2 is written, set 1 2 is written. So 1 2 3 4 5 6 elements are there, but when you check here, P of A union B, 1 2 3 4 5 6 7 8 elements are there. Means clearly these two are not equal. So we can come to the conclusion that P of A union P of B is not equal to P of A union B. So this statement we can prove by taking a simple examples. Next we shall discuss question number 8. Show that for any sets A and B, A is equal to A intersection B union A minus B, and A union B minus A is equal to A union B. There are two statements are given us to prove. Let's take the first statement, right hand side. RHS is equal to A intersection B union A minus B. This one we have to prove it is equal to set A. I am using Venn diagram, visualization of the sets to show this one, this steps, okay, so that it will be easy for you to understand how we are writing the formulas. So when we use a Venn diagram, the rectangular portion represents the universal set. There are two sets A and B, and the common portion is here. I am marking it with green color and A intersection B, and this portion I am shading it with red color, and another portion, B portion, I am shading it with a yellow color. So by using these three colors only, I am going to explain the statements. So you have to be very careful when you are doing this type of questions. So A intersection B union A difference B. Here I am writing as A intersection B. First part is same, union A difference B. A difference B means elements of A, that means this set, elements of A which are not in B, that means this red portion only, that is what A minus B. So instead of A minus B, I am using A intersection B naught. Let's check whether these two are equal or not. A intersection B naught means, intersection means common, a common portion for A circle and B naught. B naught means outside of B. Common portion for A, that is this circle, and outside of B. Outside of B means this is B circle, outside of B means this portion. That means a red colored portion. This red colored portion is common for both A and outside of B. That is what it is written, A intersection B naught. Now let's expand it, this one, that is A intersection B, this symbol union, first element A intersection B union A, then this symbol intersection, then again A intersection B union B naught. We have expanded. Then what we are going to do is, here A intersection B union A, these three sets together, A intersection B, that is this green portion, A intersection B union means together with A. So this green portion union means together with A circle, means clearly it is A. Means when we combine A circle and this green portion, means we will be getting only the first circle, A circle, that is our A, that is mentioned here. Next is the same symbol intersection, and here first A is the set as it is written, then B union B naught. This means that B, a particular set and its complement. B union B naught means a particular set and its complement. If you want that also, I will show you by using Venn diagram. See, for example, there is a set is mentioned, that is a universal set, and there is only one single set it is mentioned, that is B. And when you check here, what is given to you means B union B naught, means union means together, B means B circle, this B circle, and B naught means not B, means outside of B, and this B circle union, means together with the outside of B, means the entire rectangle will be getting B circle, and outside of B circle when we combine we will be getting the entire rectangle. That is our universal set. That is what it is written. So A intersection of A intersection U, that we can write it as A intersection U. A intersection U means you can see here itself a single set is mentioned, for example that is A, and another set is U, that is a universal set. Intersection means common for a set and its universal set, means common for a set and the universal set is clearly the particular set. This is a common portion for both the rectangle and the circle. The common portion is the circular portion, so that is the set itself. That means A itself. A intersection A we have got. A intersection A means same sets common, means elements which are common to the same set itself. So A intersection A means clearly it is A. A intersection A is equal to A. That is what our LHS. That is what we have proved the first statement. Next we shall discuss the second part of question number 8. Second part is A union B minus A is equal to A union B. That is what we have to prove. So let's take the left hand side, A union B minus A. Here also I am going to use one diagram. So U is the universal set, that is a rectangular portion. Subsets we have taken A and B, and the common portion is A intersection B, which is shaded by using the color green color. And next here when we check this portion, I will mark it with red, and another portion will be marked with or shaded with yellow color. Now A union B minus A. I am going to change this B minus A. B minus A means elements of B which are not belongs to A. That means the yellow shaded portion. I'm going to replace it with A union B intersection A naught. Let's check B intersection A naught. What is that? B, set B intersection means common for A naught. A naught means outside of A. B which is common with the outside of A. B and outside of a common portion. So B circle is this one. Outside of A means outside of this portion, these two colors. So a common portion which is common for both B and outside of this circle is this yellow portion. Very carefully you have to check a portion which is common for B as well as outside of A, that is this yellow color. That is what it is mentioned, B intersection A naught. Then let's expand it, that is A union B, it's written intersection A union A naught. A union B, it's written intersection, that is the symbol A union A naught, it's written. And A union A naught, it is quite clear. A union A naught means a portion which is together with its complement. Together with the complement. In the previous question we have discussed this one. Here when we take a universal set, this we can mark it as U, and one set it is mentioned, that is A. So union of that particular set A and its complement. Its complement means it is quite clear, it is outside of this circle. So outside of this circle together with A circle means clearly it is a rectangular portion. Rectangular portion means this is U. So A union B intersection U. That is what, instead of A union A dash we have marked U. So now it becomes A union B intersection U. Means again if you want we will show you. Okay, by using this diagram we will show A union B. A union B means two circles together. Intersection means common for this universal set. This universal set and these two circles common portion is clearly this portion, means the entire two circles, these three shaded portions. So that will be equal to A union B. If you take these circles together we call it as A union B. So that is what our right hand side, that is equal to RHS, hence the proof. Dear students, today we have discussed first 8 problems from the miscellaneous exercise of the first chapter. I request all the students to go through these questions and practice it properly. While practicing, if you have any doubt, please note it and keep. We will discuss it during the discussion session. Thank you for watching.